Good morning, everybody. This is part two of chapter 18, the calculation of pH for strong acid, strong bases, and also the calculation of pH for weak acids and weak bases. First, we will take a look at strong acids, strong bases, how to calculate their pH, and then we'll go over to the weak cases. For strong acid and strong bases, the calculation of pH is quite straightforward. Since we only need to know the concentration of H plus to calculate the pH, I have written down the formula for the strong acid to strong base concentration of H plus and OH minus here. So for a strong acids, the concentration of H plus is the same as the initial concentration of the acid. And what I mean by that is illustrated in this example here. So let's say, for example, we want to calculate the pH for a 0.1 molar HCl solution, which is a strong acid. The concentration of H plus is the same as the concentration of HCl because HCl is a strong acid. That basically means that all of the HCl will be eventually in the form of H plus. So therefore, the concentration of H plus is 0.1 molar, the same as HCl. And therefore, the pH is going to be the negative log of 0.1, which is the concentration of H plus, and that is, you can just use your calculator, negative log of 0.1 is just 1. And that makes sense because the pH of an acid is supposed to be less than 7. Now, for strong bases, the concentration of OH minus is the same as the concentration of the base itself. So, for example, for a 0.5 molar sodium hydroxide, which is a strong base, the concentration of OH minus is going to be the same as the initial concentration, which is 0.5. Then we plug it into the POH formula, and we get the negative log of 0.5 to be 0.3. So that is POH, not pH. And it's important for us to realize that because sometimes the student, they just leave the answer as 0.3, which is not true because the pH of a base is supposed to be greater than 7. So therefore, we use the second formula. pH is 14 minus POH. And that's 14 minus 0.3, which gives you 13.7 as the pH of the strong base. Now, for the second part of this presentation here today, we are going to take a look at the calculation of pH for weak acid and weak base equilibria. For the weak acid, now we have to proceed through the ICE table, which is basically what we covered in the equilibrium chapter. I is initial, C is change, and E is equilibrium. So that's an acronym for the reactions that proceed through equilibrium. Now, for the weak acid and weak bases, we're always going to set up the ICE table. And again, it's important for you to know which acid is strong, which acid is weak, so therefore you can set up the table accordingly. So here I'm just showing you an example of how to calculate the pH of a 0.1 molar acetic acid, which is a weak acid, and the Ka is given to us to be 1.8 times 10 negative 5. So we set up the ICE table. First of all, this reaction refers to the dissociation reaction of the weak acid, which proceeds through equilibrium. So the acid loses a hydrogen. Basically, that's the entire reaction. And it becomes acetate ion and H plus ion. Now, initially, we have 0.1 molar concentration. Nothing here for the acetate and nothing here for H plus. And then as the reaction proceeds, the reaction basically, it dissociates into negative X plus X plus X, and at equilibrium is 0.1 minus X, X, and X. Now, the The Ka, which is the equilibrium constant for this dissociation reaction of the acid, weak acid, is basically the concentration of the product at equilibrium divided by the concentration of the reactant at equilibrium. So it's important to recognize that these are equilibrium concentrations, not the initial concentrations. The K is given to us, 1.8 times 10 to the negative 5. We just plug in the numbers here. The concentrations are X, X, and 0.1 minus X, as you can see in the equilibrium row. So that's X squared divided by 0.1 minus X. So let's just go to the next slide. And as you can see, the last equation is a quadratic equation. So basically that means we have a power of X squared in the equation. That's a quadratic formula. In order to avoid the use of the quadratic formula, because it's time consuming and we actually rather to avoid most quadratic formulas, they're lengthy and also we are more prone to make mistakes when we use a quadratic formula. We use a simplifying assumption. What is that assumption? The assumption is that X is small, and therefore we can say in the denominator of that equation 0.1 minus X becomes almost equal to 0.1 because X is smaller than 0.1. So since X is small, that's our assumption, then 0.1 minus X becomes 0.1, almost equal to 0.1. That's why I have that almost equal sign there. Now the last equation becomes 1.8 times 10 to the negative 5 equal to X squared divided by 0.1, and X squared is basically the cross product here, and then X becomes the square root of that number, which is 1.8 times 10 to the negative 6, and that's 1.3 times 10 to the negative 3. Now, we always have to check the assumption. So in order to check the assumption, we use a rule called 5% rule. So basically 5% rule tells you that the H plus calculated, which is your X, divided by the initial acid concentration times 100% must be less than 5% in order for the assumption to be valid. If that's not the case, then we have to reject the assumption, go back to the initial formula and use a quadratic formula. Okay, but in most cases, X is actually small enough for the assumption to hold. So let's check the assumption. So again, the X calculated, which is this number, divided by the original or the initial acid concentration times 100% must be less than 5% for the assumption to be valid. And therefore, we can just justify not using quadratic formula. Okay, so let's go to the next slide. So here, we are basically calling that the whole entire formula H plus divided by the acid concentration times 100%. We're going to call that percent dissociation, so that we can, for sake of saving time and also efficiency, we're just going to call it percent dissociation instead of just referring to it as this divided by that times 100%. We're just going to call it percent dissociation. So let's calculate the percent dissociation for this specific problem. So therefore, the percent dissociation becomes the H plus that we calculated divided by the initial concentration 0.1 times 100%, and that gives us 1.3%. And since 1.3% is less than 5%, therefore we conclude our assumption is correct. Now, so again, I'm just reiterating the rule that 5% rule has to be satisfied in order to avoid a quadratic formula. So since now 1.3 is less than 5, we are okay with the assumption. But if it's not, if this percent dissociation is greater than 5%, we have to go back and use a quadratic formula. Okay, so let's go back to the equation again. Now, the pH equation, basically, negative log of H plus gives you the pH. We calculated the H plus to be 1.3 times 10 to the negative 3, and the pH becomes negative log of that, which is 2.89. Now, this is very important. This basically tells you that that there's a shortcut when the 5% rule is satisfied, we can actually calculate the H plus concentration by taking the square root of Ka times the initial acid concentration. And that shortcut is demonstrated down here. So if you want to redo the previous problem using this shortcut, so you basically write down H plus is equal to the square root of the Ka, which is given in the problem, 1.8 times 10 negative 5, times the initial concentration of the acid, again, given to us, 0.1. So if you multiply these two numbers, take the square root of that, you get 1.3 times 10 negative 3. And pH is simply negative log of that, 2.8. So they are the same. So you can either go through the ICE table or you can just use the shortcut. Now, the shortcut, again, is valid when the 5% rule is satisfied. So now, for the weak bases, the calculation of pH, again, is parallel to the calculation of pH for weak acid. We have to set up the ICE table. Okay, so let's go to the next slide. Okay. So, to demonstrate the concept of the pH for weak bases, I have this simple example. What is the pH for a 0.25 molar NH3 solution? NH3 is ammonia, is a weak base. The Kb for ammonia is 1.8 times 10 negative 5 is given to us. Now, it's just a coincidence that the Kb for ammonia and the Ka for acetic acid, they happen to be the same. It's just a coincidence, okay? All right, so again, we set up the ICE table. Now, the reaction now is a little different for the acetic acid. It's a base, so therefore we must indicate the source where the hydrogen is coming from, and the source is water. So we are including water in the base dissociation reaction, okay? But for the acid, we didn't have this water, okay? For the acid dissociation reaction, it was just the acid producing the negatively charged and the positively charged ion, okay? So for the base, we have to include the water, even though it doesn't contribute in the overall equilibrium calculation, but we still have to show it in the reaction. So the reaction is going to be NH3 plus H2O, producing NH4 plus and OH minus. Now, again, this is a base reaction, so the base will grab hydrogen from the water, becomes NH4 plus. Water is left with one less hydrogen, therefore OH minus. 0.25 initial, 0, 0 for the product, minus x plus x plus x. Equilibrium is 0.25 minus x, 0 plus x, 0 plus. So x and x here. So these are the important numbers we need to have, okay? Now, remember, the water does not contribute to the calculation, so therefore we just leave it blank, okay? We don't write anything for water. As a matter of fact, the concentration of water is 55.5 molar, and it's a constant, so therefore we just basically ignore it, okay? Now, I've also indicated here again that the Kb and for NH3, Ka for acetic acid are the same, it's just a pure coincidence. Now, the Kb, so we go back to the ICE table again, the Kb is the x squared divided by 0.25 minus x, so in other words, the product concentration of the product divided by the concentration of the reactant. So we have x times x divided by 0.25 minus x. And that's this equation here. The Kb is given. Again, we make the assumption, so as it stands, this is a quadratic formula, but we want to avoid the use of a quadratic formula. So what do we do? Again, like the case of a weak acid, we make the assumption that is x is smaller than 0.25, so therefore that becomes just 0.25, okay? Now, let's go to the next slide and see what happens to the rest of the calculation. So, okay, now let me just bring this down a little bit. Yeah, okay. Now, the the equation now is x squared divided by 0.25 instead of 0.25 minus x. And that's equal to kb. So if you cross multiply, you get x squared equal to that. Therefore, x becomes what? The square root of that product, right? So take the square root and you get 2 times 10 to the negative 3 for the concentration of x, which is basically OH minus. If we check the assumption again, the OH minus that we calculate here divided by the initial concentration of the base times 100% gives you 0.8 and 0.8%, and that is basically less than 5%. POH is negative log of OH. Again, remember for base reactions, you always calculate the POH first, and then 14 minus POH gives you the pH, which is 11.3. Now the shortcut for this is that Kb times the concentration of the base, okay? The square root of that, of course. And if you want to go ahead and do that, you see that this is really Kb. That's the concentration of the base, and therefore that gives you OH minus at the end. So this is the shortcut that is demonstrated by this equation here, okay? All right. So therefore right now what we have is basically how to calculate the concentration of the acid, weak acid and weak bases, as opposed to strong acid, strong bases. Now, the last thing we need to know on the calculation of pH is it relates to the calculation of pH for salt solutions, okay? And actually, I have taken one sample problem, which is a very good sample problem on page 822, and that sample problem basically, demonstrates how to use the concept of pH for the calculation of the different concentrations when it comes to salt solutions. So this is the problem: pH of a 0.25 molar sodium acetate solution. This is a salt solution, 0.25 molar concentration. It's called sodium acetate. Now, sodium acetate is a salt. All salts are a strong electrolyte, so therefore it dissociates into a negatively charged acetate and a positively charged sodium ion. Now, so I've basically described here that this is the reaction that is taking place in water, and the acetate ion is a weak base that will react with water. That reaction is called hydrolysis. So basically, the sodium acetate the acetate ion, in other words, this ion, will be hydrolyzed, and that is the basis of the ice table here. Okay. Now, I've also indicated that Na plus has nothing to do with this reaction with the ice table because it's a spectator ion. That means it's really never involved in the reaction. So we always take the negatively charged ion, we react it with water. It's called a hydrolysis reaction. Excuse me. It's called a hydrolysis reaction. So the negatively charged ion is going to react with water, and it's going to grab a hydrogen from water. So therefore that becomes acetic acid, and water is left with one less hydrogen, OH minus. And we set up the table for it: 0.25, 0, 0, minus x, 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 0.25 minus x, x, x. Now, one thing that you should note is, and it's very important, is described here. This is a base reaction, okay? Now, in the original problem, which I have forgot to include, the Ka for the acid must be given to you. So the Ka for acetic acid is 1.8 times the negative 5. Now, this is a base reaction. You need to know the Kb for this reaction, the magnitude of the Kb for this reaction. We're going to use this formula, Ka times Kb equal to 1 times the negative 14, which I already gave you in the beginning of the discussion of acid-base equilibria in the previous video. Okay, so Ka times Kb is 1 times the negative 14 for a conjugate acid-base pair. What is the acid? What is the conjugate base? The acid is acetic acid. The base is acetate ion. That's the conjugate base. So this Kb relates to this reaction. The Ka is just for the acid for this. Okay, so CH3COOH and CH3CO minus are the conjugate acid-base pair, which we already defined in acid base part 1 of this video. The Ka for the acid is given to us 1.8 times 10 to the negative 5, and therefore the Kb is simply 1 times 10 to the negative 14 divided by that number, which gives you 5.6 times the negative. So I'm using this formula, which you need to memorize, with the emphasis on the fact that the Ka will be given to you. So therefore, you can easily calculate Kb. Okay, so what do you do with that Kb? So let's go to the next next slide. And if I can get that, yes, here we go. Okay, so so again, I've indicated here that this is a base dissociation reaction, so therefore you need a Kb, not Ka. So the Kb is basically 5.6 times 10 to the negative 10, which was already calculated in the previous page. So it's that is equal to x squared divided by 0.25 minus x. Now that comes from the ice table. These are equilibrium concentrations in the E row of the ice table. Now we are going to assume that x is much smaller than 0.25, so therefore that becomes what? That becomes this equation, right? We just ignore x here in the denominator. And then x is basically the Kb that we calculated here times the initial concentration of the salt, and then take the square root of that. And that's, remember, x in this ice table now is OH minus, is not H plus, okay? H plus, x is H plus when you're dealing with the acid dissociation reaction, but it's OH minus when you're dealing with base dissociation reaction. So x is 1.2 times 10 to the negative 5 when you take the square root of that product. Okay. So we are going to check our assumption. The x calculated divided by the initial concentration times 100% is actually 4.8 times 10 to the negative 3. And that is less than 5%, so therefore our assumption is justified. POH is negative log of that number, which is 4.92, and pH is 14 minus that. Again, don't forget to do 14 minus POH to calculate the pH. Don't just leave it as POH, because the question is asking for pH, not POH. So you have to do a second equation, 14 minus POH, and you get 9.0H. Again, you can see that the pH of a base has to be what? Greater than 7, and that is correct. That is consistent with this number here. Now, to summarize, the shortcut for calculating the pH of a salt solution is that OH minus is Kb times the initial concentration of the salt, and also keep in mind that Kb is 1 times 10 negative 14 divided by Ka. Okay, everybody, I hope this was a useful video for the last part of chapter 18, acid-base equilibria. And I've kind of changed the setup to take this video. I hope that was not a problem in you you seeing this this concept of the acid-base equilibrium more clearly. So I will again I will check back with you on Thursday of this week at 11 o'clock, all sections at 11 o'clock, to see if you have any questions, and just go over this and review it one more time. Have a great weekend, and I'll post this as soon as I can.